Drilling is more an art than a science. A good driller, the man on the brake handle, the man who's actually running the rig, knows more about what's going on downhole than anybody else on location. This particular rig is a rig that's used for minerals exploration coring work, but we've got it on a hydraulic sub-base to get it up off the ground, and we're using it with conventional drilling equipment on this abandonment. On this well, we're going to clean out the existing casing and well bore until we reach at least the shoe of the casing that's over 300 feet deep, and then we're going to put cement in the open hole below the casing, and then we will cement the well bore from the shoe of the casing back up to surface. Bits are what's used to drill a well almost all the time. Bits that you saw are tri-cone bits. The bit has got 3 cones on it, and they're tapered wheels mounted on bearings and set up so that when you set the bit on the bottom of the hole and rotate it, all 3 wheels rotate also, and the teeth on those wheels is what gives you your digging action. We set a portable pump down in Clear Lake and put in irrigation line from that pump up to the hill above the rig where we have water storage tanks. And those tanks were filled with water from Clear Lake, and that's what we're using to mix our mud with, and all of the water around the rig comes from those tanks. Drilling mud is the major component of well control. Mud is pumped out of the pits, down through the drill pipe and the drill collars, out through the bit, and circulates back up around the drill pipe and drill collars to surface, where it's treated and recirculated.
After clearing the old access roads that had grown in over the years, the team moved in the 2 main pieces of equipment needed to plug the wells, a workover rig and a logging truck. The workover rig, which is placed directly over the well, is a piece of oil well maintenance equipment that can perform various functions, such as hoisting and removing pipe sections. The logging truck, situated a few feet away, houses an array of geophysical monitoring equipment that reads signals from instruments lowered into the well via a 10,000-foot or longer cable spool. These instruments send back info to the cab that can be analyzed by the team to determine the condition of the well and the surrounding geology.
These wells, of course, have been abandoned for several years, and we sometimes have difficulty getting tools or bond log tools inside this tubing. Iron sulfide, paraffin builds up on the inside of the tubing, and we use an open-end bit that we wash water down through to try to clean out the tubing in order to get the bond log tool down through the tubing.
Once the production tubing was finally opened up, the team could then assess the various pieces of tubing and casing in the well. On a typical well from the era, a borehole was usually supported by a well casing at least 4.5 inches in diameter. Inside the well casing was the production tubing, usually 2 inches in diameter, which delivered petroleum product to the surface. Near the bottom of the well, which was anywhere from 500 to 600 feet deep, the backside of the casing was cemented against the borehole wall. The backside surface of the production tubing sometimes was also cemented to the inside surface of the casing. Between the backside of the production tubing and the inside casing wall, a mechanical or rag packer was usually inserted and sometimes cemented in place. The purpose of the packer was to stop the flow of any oil outside the production tubing.
A solid sampling protocol is crucial to success at the Pemmico Superfund site.
One of my concerns actually as a project manager is that we do enough sampling. So we have data points that actually have a pictorial view of what happened before we started and a little bit more picture of it, if you will, a much more detailed picture of what happened. And then at the same time, we're sampling throughout the heating process, so I can look at results on both a weekly basis to determine how much mass is being removed, concentrations, how they're changing or not changing. And then when I get to the end point, or the end game, if you will, I will feel comfortable about making a decision about turn-off.
Before any injection could take place, 100 small-diameter micro-wells were drilled inside the mill foundation to serve as injection and monitoring points. The 100 by 200-foot grid was based on delineating an area where TCE concentrations exceeded 1 part per million. The wells were drilled perpendicular to the prevailing groundwater flow and were staggered to ensure all of the plume would receive equal concentrations of the injected solution.
A typical steam injection system works like this. Steam is piped in from a generating plant or portable boilers brought onto the site and is distributed to a series of injection wells, which can be hundreds of feet deep, reaching through the unsaturated and saturated zones. At the base of the treatment zone, the steam flows horizontally from the wells, working like a hot plate, preventing the plume from migrating downward. The increase in temperature and vapor pressure causes the contaminants to vaporize and/or move more easily as a liquid. The displaced compounds are then driven to vacuum extraction wells, where they are brought above ground and treated with equipment on the surface. Some contaminants are also destroyed below the surface through oxidation by the injected steam. This process is known as oxidation or hydrous pyrolysis.
The oil boom that swept across the American West early in the 20th century provided fuel for our growing nation and helped shape the character of the West. For the thousands of enterprising drillers and speculators that rushed to the oil fields, fortunes were often made and lost in a matter of days. Unfortunately, this boom and bust cycle has left a legacy of abandoned wells and refineries in the region.
The electrical resistance between electrodes around the site is measured, which generates a near real-time cross-sectional snapshot of the temperature between different parts of the site. This allows engineering corrections to be made to the injection and extraction wells to increase productivity. In fact, productivity at the SRS site has gone beyond the expectations of everyone. In just 1 year, over 70,000 pounds of TCE and PCE have been removed.